Hello everybody. I hope I'm live. Oh, I think I'm live. Yeah, I'm live. All right. So it's been a while. It's been like 200 days since I last streamed. I hope my audio is fine. I think it is. It might be on the higher end, but yeah, I look fine. All right. So a lot of things happened. I graduated college. I switched to Arch Linux. Yeah. So so I want to continue. So it's been like, but yeah, I'm a bit rough. All right. So in this string, I'm trying to start a new thing. Like I want to learn everything about modern LLMs. When I say everything, I made an outline uh, of what I have to learn to like completely learn everything about large language models in general. So we have the basic things, but there are also the modern advanced things like different attention variants, wait time, initialization techniques. When I say initialization techniques, there are different initialization techniques which would work differently for different system, different data set maybe, things like that. So I want to be able to learn all of them very well, in depth. So I made a plan. This is available in GitHub. I probably link that in the description. And yeah, that's the plan. So for that, Uh, initially, I want to start reading papers. So my plan is to read the papers on stream and study off because I think I will be more better. It will be better if I study off stream. And reading papers is fun. But today, I'm going to read. Attention is all you need because this is a paper that deserves multiple reads. So it's been a while since I read papers. I think the last time I read paper was something similar to 100 days ago. Uh, yeah. So my audio is hopefully fine. Yeah, audio is fine. Mm, yeah, I think that's it. Just start reading the text. Attention is all you need. This will be probably I'll put all these things into a new what is it called? Mm, I'll put all this live video into a new what is playlist? Yeah, that was what I was going to say. I'll put all this into a new playlist and yeah. So we'll start from scratch. Attention is all you need. By Ashish Vishwani, Google. The dominant sequence transaction models are based on complex, recurrent or convolutional neural networks that include an encoder and a decoder. The best performing models also connect the encoder decoder to an attention mechanism. We propose a new simple network architecture. The transformers based solely on attention mechanism, dispensing with recurrent and convolution entirely. Dispensing recurrence and convolutions entirely. Experiment and two machine translation tasks show these models to be superior in quality while being more parallelizable and requiring significantly less time to train. Our model achieved this score, blah, 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 on blue. Uh, on WMT English to French translation, our model established a new single model state of the art. Okay, sure. We know how good transformer is, no need to glaze it. We show that transformer generalizable to be used in other tasks by applying successfully to increase constituency passing both is okay, sure. It's present and that's cool. All right. So um Mm, I just try something like a paper. Yeah, I used to read this paper, and I think she on it was the 10 months ago. That's neat. This is a note I made back then. New architecture used in drops RNNs, CN concepts, improve validation, figure global dependencies. Ability to understand long range dependencies in the network is far superior to other models. Ransomware is the first transduction model, relying on self attention to compute. What is transaction model? Jimmy, transduction in AI. Do something? Oh, it's happening. Yeah. Right. It is happening. What is transduction here? I'll do CBD for one. A transaction refers to a process of converting input sequence into output sequence. Oh, it is sequence to sequence learning. All right, sure. It's a different name for range. Okay, okay, sure. Equal contribution. Oh, equal contribution by everybody, huh? Recurrent neural networks. Long-term, long short-term memory. LSTM. And GATE GRU have been established as state of the art for sequence modeling. Yes, sure. Numerous efforts have since continued to push boundaries. The current model typically factor computation along the symbol positions of the input and output sequence. Recurrent models typically factor computation along the symbol positions of the input and output sequences. Okay, aligning the positions to steps in computation time, they generate a sequence of hidden state h as a function of the previous state h t minus 1. Yeah, yeah. Given h of t minus 1, they generate h. Sure. And percent t. This inherently sequential nature precludes parallelization with training examples, which becomes critical at long sequence length. Yeah. R9s cannot be parallelized. Recent work has achieved significant improvement in computation efficiency due to factorization tricks and conditional computation, which also while also improving models' performance. Fundamental concern of sequential computation, however, remains true. So the primary problem of RNN, CNN, CNN, LSTM, and GRU is that they cannot be parallelized. I mean, why am I putting CNN here? This is text, right? So not CNN. It cannot be parallelized. Attention mechanisms have become an integral part of compiling sequence modeling and transduction models in various tasks, allowing models of dependencies without regard for the distance in the input and output sequence. In all but a few cases, however, such attention mechanisms are used in conjunction with recurrent network. The attention is used with RNNs. Sure. In this work, we propose transformers. They model architecture ensuring recurrence. And instead of relying entirely on attention mechanisms to draw global dependencies between uh, output. Yeah. Relying and yeah, this is the main thing. Right. Right. Oh, sure. Ooh. Okay, another was a thing. Yeah, this is the main thing. relying entirely on attention mechanism to draw global dependencies between input and output. That is the gist of attention mechanism. The transformers allow significantly more parallelization and can reach new state of the art in translation quality. Background. I mean, mm, Fonda's neural GPU, more number of operation record just very high, I guess. Just makes it difficult to learn dependencies. Yeah, I mean, we know the problem before transformers, right? Um, there was like the vanishing gradient problem where it is very hard to remember long context. It's not very hard. It's impossible to remember long context using RNs or uh, even LSMGRUs. You cannot remember very long context. You cannot. You just cannot. Transformers just made that possible, right? Um, so today Germany has like a million contexts, so and I think Llama for Maverick has even higher ones, 10 million or something. So this was made possible because of Transformers attention mechanism, where the model inherently focuses its attention on various parts of the signals. So each token attend to a different token at different levels. That's a yeah. All right. So self-attention, called intra-attention, is an attention mechanism relating different position of a single sequence in order to compute a representation of the sequence. Sure. Self-attention has been used successfully in various tasks, including orchestral, end-to-end memory networks, and based on ARM mechanism instead of sequence orchestral. To, to the best of knowledge, our transformer is the first transaction model relying entirely on self-attention to compute representation of its input and output without using sequence aligned RNN. The following sections will describe transformers model architecture. So here we have this transformers, right? So we have the input. It goes to an embedding layer. So this embedding layer initially contains random embedding. So this input layer contains tokens, the input tokens, which are converted into numbers. Not numbers, indices. Indices of the vocabulary, indices from the vocabulary. So this indices is converted to embedding. Right? How is this embedding converted? Essentially, this is also trained. This is actually trained during the whole thing is trained. Right? The whole thing is trained in one go. So embedding is not separately trained. So eventually, this embedding layer will learn to represent each word as a bunch of numbers, such that it will remember the essence of the word. Right? That's the basics of embedding. So then into that embedding, we'll add a position encoding, which is the position information. So the first word will get the number one, second will get number two. Not literally, but essentially, right? Then this will go into the encoder. At the encoder, this input embedding will be split into three parts: the query, key, and value. In fact, that is not true. That's not true. So in this layer, the embedding is split into multiple heads. It's just copied multiple times. Let's say there are 8 heads. So we have 8 copies of the input embedding, and each of the embedding is split into three parts: query, key, and value. So this query, we get the query by multiplying uh, input embedding by query matrix question mark. I'm not sure. Wait, how do we get the query made in a transformer from the positional embedding vector? Query is not applying some program, but on some of the input token embedding and the position. Oh yeah, that's what I meant. But sure, yeah, positional embedding probably only means. Oh, okay. I thought the sum of input embedding and the positional encoding is the positional embedding, but apparently it's not. Okay, positional encoding and positional embedding the same thing. Sure, makes sense. Yeah, we take the sum. Sure. Then we do a linear projection to query. Query is input times WQ. WQ is the query weight matrix to produce query weight. Yeah, that's exactly what I thought. So we take this thing and matrix multiply it with the query matrix, we'll get the query. Key matrix, we'll get the key. Value matrix, we'll get a value. So I'm going to copy you. In fact, I'm not going to wait, what? I don't want that. But yeah, I'll take you. And what accelerator? Oh, I'll put you here. So what happens? At in what happens is so here there are multiple heads, right? So there is a head one, there's a head two, etc. Nth head. Let's say eight heads, right? So that is H8. For each head, we will get a different QKV values, query, key, and value. For each of the head, there is a separate QKV matrix. And by multiplying this, like the sum of this guy, that is what we have here. I mean here, this input. By multiplying this with the subsequent QKV matrices for each of the head, you will get the QKV vector for each head. Now, what is the significance of QKV, query key and value, for each head? So, essentially, in a what do you call it, very high level view, this Q asks a question. That is why it's called query matrix. This key answers a question, and this value is used to find the final value for both of these guys. I'll explain. So what is done is there will be multiple tokens. Uh, let's explain high level, right? So the catch, chat, and the match, the classic sense. We have each of the what do you call it? Mm, uh, oh, each of the so let's say Hmm, we will have a bunch of inputs here. Let's say we have 10 words, right? 10 words. Or not 10 words, 10 tokens to be clearer. Let's for now we'll assume every word is a token. So the shape of this thing will be something like 10 comma, right? It will going to input matrix, and let's say each token is represented by 512 numbers. Then we add first information to this. So essentially what will come out is like something like 512 comma 10 or 10 comma 500, depending on how you want to arrange it. I don't know the mathematical way to correctly represent it, but I think both works. Let's start off. Uh, Now what? Mhm. Now what? Uh, so will we have a hmm, I gave a transformer 10 words, 10 tokens. If each token after embedding needs 512 numbers to represent it, the shape that goes into the multi-head attention layer will be 10, 512, correct? I think this is correct, almost correct. If you pass 10 tokens, which is represented by 512 dimensional vectors after embedding, then for a single example, not batching, the shape is 10, 512. If you're using batching, common practice, okay. Uh, so this is as for, yeah, batching to update the weights all one go. Yeah, sure, sure, I get it. So we are correct. Sure. Now, at the multi-head attention layer, how will the QKB be calculated? Be calculated. What is its shape? And will, mm, yeah, it's active. So the input layer, sequence length, embedding dimension. Yeah, this is the input is projected to three separate spaces using linear layers. Input into WQ. There are number of head, usually dk equal to dv, number of dimension. After linear projection, before splitting heads. After splitting heads, it becomes BHLDK. Oh wait, um, the batch size doesn't matter, doesn't change. What is L? Sequence length. That also doesn't change. Yeah, it's add heads. Then the embedding dimension actually reduces. Oh, okay. I thought every head will get the same input, but not really. Every head will get a part of the input in it. Hey, this thing is not all. I shouldn't have put this right now. And look, it's super slow. I hope the stream is not lagging. Hmm, stream's not lagging. Anyways, hmm, so yeah, so each head will get a part of the what embedded dimension. So, that makes sense. Sure. Now, yeah, so this will be the shape. Also, h into dk will be e. That is something else. That's another thing. So is all our doubts clarified? Yeah, it is. So this will be the shape of the QKV split, right? Mm. Mm. So what will happen for this thing is each token will attend to itself. Each token, let's say, let's take the token cat. It will have a query, key, and a value. Similarly, let's take match. It will have a query, key, and a value. On will also have a query, key, and a value. D will also have a query, key, and a value. Now, um, let's start with the cat. The cat will have a query, right? This query essentially will ask each of these guys, hey, how much are you related to cat? Now, how is this thing mathematically done? By matrix multiplication. I will explain that soon. So this will essentially ask a question. Hey, I'm asking a query cat. How many of you will respond? This match will respond using the key value, using the key matrix. This on will also respond. I mean, all of these guys will respond, obviously. But the key, so I will mathematically do it. So what happens is this query and the key are matrix multiplied, and it is divided by the root of the dimension. Um, since this does not have big impact right now, I'm going to rub that off for easiness. Right, but okay. So query and key are multiplied, matrix multiplied. So dividing that, essentially this will give a probability, like a number like zero point 0.8 or zero point 0.2 after division by the root of dimension. But sure, in fact, why not? I will put it there. So this key values for each of the other values. In fact, for this also, they will give a value. For example, the cat and the mat are related because cat is sitting on the mat. So this will have a high number. On will also have a high number because it is the action which is sitting on the mat. Sat will have even higher number because it is actually sitting. Right? T will have a lower number because these there is no much relation. This thing this k will also have a lower number. Now a reminder: how does what is this lower number? This calculation query into key divided by the root of dimension. Sure. Now what will we do? Now we multiply that with the value. Multiplying this thing with the value will tell us the attention score of a token with another token. So this is the self-attention part of the transformers, which is arguably the most important part. So now this is now let's read that part and hopefully I didn't miss anything. The transformer follows this architecture using shaft self-attention point star. The most competitive neural transaction model have an encoder decoder structure 5 to 35. At each step, the model is auto-regressive, ensuring the previously generated symbols as additional input. Encoder and decoder. The encoder is composed of a stack of 6 identical layers. So this thing will happen 6 times. We can write over this, but I know that. So this thing will happen 6 times, right? Yeah, yeah, that is the 6 times. Each layer has two sub-layers. The first is a multi-layer attention. I thought this is selecting area. You are not selecting area apparently. All right. The first is multi-layer attention. Second is simple precision by fully connected feed forward network. Yeah, this part. So we do the multi-head attention. So it will extract important parts and then we will pass it through a feed forward layer. And this feed forward layer is where every what input the this will give a better representation of the input to this layer and all the calculation, all the what matrix multiplication into conversion of input into output happens in the feed forward layer. In fact, this is a bigger part, and this will contain all the weights, which will contain the things that the transformer actually learns. We employ residual connection around each of the sublayers. Oh, okay, every sublayer has a ResNet. Cool. Followed by layer normalization. The this is post layer normalization. At least this is what it just said, but I'm pretty sure in the implementation they have done pre-normalization. That is I've heard that is a bug in this paper. So this is actually mm, followed by layer normalization. So this is actually a bug in the paper. Fun fact. Output of sublayer is layer normalization of x into x plus sublayer. So x plus sublayer and we do yeah. What is x? This is x. What is sublayer? This is sublayer. So we do sublayer of x, that is this output, and we add that with this thing. So that's addition. And then we normalize everything. Cool. That's easy to understand. the function implemented by the sub-layer to facilitate the serial connection of sub-layer in the model as well as the embedding layer produce the output of dimension 512. That's very good. Hmm. I kind of want to write the whole thing down, call the whole thing. It's a very simple transformer for doing a very simple thing, I guess. And for translation, I mean, this thing is made for translation, right? Maybe I make a default only model for text conversion. That's it. So essentially, there are three types of transformers. This is the encoder, this is the decoder, right? So there is encoder only transformer, there is decoder only transformer, and there is the encoder decoder transformer, which is this. So the encoder only transformers is good in task where the input has to be clearly, very thoroughly read. For example, like classification, read the text and classify it into something. Right? In such tasks, encoder transformers will be the best. Summarization, no, sorry, not summarization. Like answer the question based on the content, based on the text. So that's a question. That's a situation where encoder transformers will be very good at. Now, at the same time, decoder transformers are good in situations where the input has its value, but it's not the most important thing. The answer is the most important thing. For example, text generation. So, why is the sky blue? The question is important, sure, but everything, but the answer is more important. You just have to go through the question only one time, right? But in a situation like what uh, answer the question based on the text, you probably have to go through the text a lot more times. You have to properly parse the text, properly read the text. You're just answering the question, like basically causal text generation. So in such situations, decode only models are found to be better. Um, Now there are situations where both are important. The example is translation. So you read a text, you translate into another text. So here, like, both are equally important. So in such situation, the encoder decoder transformers are better. Now, now that I've said this is not necessarily true these days because today all the focus has gone to the decoder only model. So all the advanced techniques, etc., are made for this. So these days, but decoder only models are like outperforming everything else. But the initial theory was this: each type of transformer has its own advantage. So that's that. Now, mm, where are we? Right now, decoder. So the encoder will give a really good input to this thing. Now using this and then initial output embedding this. So the same multi-head attention thing happens here, but it is matched here so that the token will not attend to the future token during training. You will probably read that in the future. Now this, yeah. So the input will go into this. In fact, the query and the key will go from this, and the value will come from here. So all this, guys, will go through a multi-head attention layer into the feed forward and will predict an output. This output, so here let's say we are generating a text. So the cat, right? This is, let's say this is the input. So the cat goes in here, right? It will come through here. The query and key value will here, and initially there will be a sample output embedding. Like let's say start, a starting token. Let's say a token called the start. This is for sample, for initialization purposes, let's assume. Right? So that will go as the value and it will generate the probability, the get set, right? So the text has become the get, the start token, set, the get, start token, and the set. Now this will this new word will go here, and it will like auto recursively loop here till the end token is generated, and when it is generated, the program is uh, forcefully shut down. So that's the gist of transformers. And I think I that have explained everything. Now what we did I miss anything? Let's read. The record is also composed of a stack of six identical yeah, also this also runs six n times. So actually this is like these guys are very big, right? So this goes through all this and then loops, not just one layer. In fact, each of these has three blocks, right? So each one of them has three blocks. So this is like a big thing. That is why generation of each token in modern LLMs takes time. In fact, this is a very small setup. Modern LLMs are way bigger. So in fact, it will have a different architecture. So we can even say that, right? In addition to two sub-layers in each encoder layer, the decoder inserts a third sub-layer, which performs multi-head attention. It will also modify the self-attention sub-layer to prevent the positions from attending to subsequent positions. Yeah, this is done during training to prevent the token from attending, like, um, to prevent the token. Where is it? During training, uh, like the token, me, sorry, I guess the token B should not attend to the. I mean, let's say during training, this token should not attend to the future tokens because this token has not been generated yet, right? So that is we actually mask it there to prevent that from happening. Attention. This mask combined with the fact that output embeddings are offset by 1% shows that the prediction of the output for person I depends only on the non-input. So, attention. So attention function is described as mapping query and key. Mapping a query and a set of key values to an output. Like QKV are all vectors. The output is a weighted sum. So we matrix multiply Q and K, and then we scale it. Then max this is optional. Then we take the softmax and matrix multiply that thing with the V. Oh yeah, so this is the code. So we multiply query and the key, right? Oh yeah, divide that with the V. So okay, we also take the softmax here, right? Okay, I forgot that, man. I'm sorry. Yeah, we also take the softmax of the whole thing before multiplying that with the V matrix. Yeah, that's also I forgot that. So actually, this doesn't necessarily have to produce the probabilities, but softmax of this thing will definitely produce a probability. Right? Yeah, that's true. The two most commonly used attention functions are additive attention, dot product attention, statistical algorithm. Okay, sure. While for smaller usage, the two mechanisms of assembly additive attention outperforms dot attention. Yeah, there are different types of attention. In fact, I want to learn about the even modern types of attention. So I will learn about that. Multi-head attention. Instead of performing a single attention, we find benefits to linearly project the query key values h times with different linear projection dimensions respectively. On each of these projected version of the query key value, okay, so a head. Okay, I forgot to talk deeply about heads, right? So we will have each head. So all these things, right? Uh, all these things happen in one head. It's the core. All this happens in one head. Now we have the second head, right? The same thing happens in the second head. Same in the third head. What is actually different? Well, each head receives a section of the input embedding. So if 518, right, each of these will get 500, I mean 512, 512 divided by 8, right? Which is, what is that? 512 by 8, 64. Each of these guys will get 64 numbers for each of the token. So it will learn one fact about the that part. Similarly, each of the head will learn a different thing which is relevant for the what for answering this question for doing the computation, right? So in a high level view, what happens is the head one will learn the cat sat where, right? So it will ask kind of this query will ask kind of that question. The head two might ask what sat where, right? So it's a cat. The third question will like, what did the cat do on the match, right? So sat. So each of the head will intuitively each will ask a different question, and by combining all of these information, our model will learn. No, it's not done. Honestly, this is not what happens. Each head does not like learn a very like what's that, right? They just learn some very vague concept, the sum of which will give a really good output. So to for us to understand easily, that's why I said one will ask a very one type of question, other will ask a different type of question, and so on. They will just learn vague mathematical, not mathematical, vague concept related to the words. It will ask vague question, and the key will give out vague values, all of which happens in such a way that everything works out very well. Isn't that cool? That's attention. Now, dot product attention, we divide up with multiply with this value, sure. Yeah, here. Instead of performing single attention, we do with multiple heads, or on each of these predictive versions of UKV, then we perform the attention function in parallel. These are concatenated and once again projected, resulting in final values as depicted in figure 2. Sure. So multi-head values. So finally, we take the output of each head, which will be the softmax of value function, value vector, and we concatenate all of those guys and multiply that with W. And W, I think, is a future layer, right? Has to be where, where W, where the projection parameters and is it? Sure. Yeah, it has to be this. No, it's not. What is W0? WO? Um, it's probably, I think it's just a normal layer. I think it's a linear layer. Okay. Um, I'll ask this guy. Hey, what is WO? Is it a linear layer after I mean, in fact, I will not ask it because it might say yes. You're absolutely correct. I'll let it answer. Learn math. Learn the weight matrix using multi-head mechanism. Yeah, it is a linear law. Combine the information and brings concatenated result back to model's dimension. Yeah, it's a linear law. Nothing else. Application of attention. Encoder decoder attention. Sorry from encoder contains self-attention layers. Similarly, self-attention layers in the decoder allows each person to decode. Okay. So what does the attention do, right? In the encoder decoder layer, the query comes from the previous decoder layers, and the memory key and the value come from the output of the encoder. Yeah, this part, right? Uh, the encoder contains self-attention layers. So this is used to generate a good question. This is used to generate a good answer. This is the mixer, right? Self-attention in the decoder allows each person to attend to all person of the decoder. We need to prevent left-dead information flow in the decoder to preserve autoregressive property. We implement this inside. Okay, searching out minus infinity. Okay, I think this is for training purpose. Sure, it is. Yeah, question-wise straightforward lab. In addition to attention sublayers, each of the layers in encoder and the decoder contains a fully connected feed-forward layer. Ta-da! Sure. Similar to other sequence instruction, we use learn embedding to convert input tokens into output tokens. We multiply by root of d. Person encoding. So yeah, this is how person encoding is done. For each even person, we will take sine of this value. For all persons, we will take cos of this value. This is actually older technique. These days we will use rotary embeddings or partially rotary embeddings. So we will learn about that in the future. So these are like older ones. We will not. I'm not reading that. Why self-attention? Hmm. One is the target computation. People are. Another is the amount of computation that can be parallelized. The third is the path length, which is long range dependency. Yeah, long range dependencies are well represented through attention. Computation complexity is actually very high for self-attention. In fact, it is so high as n square. Those who know like data structures. So one aspect of recent advancement is trying to remove or make self-attention part more uh, efficient. Learning long-range dependencies is a key challenge in many sequence translation tasks. True. Yeah, we know that. Oh, wait, what? As ordered, self-attention layer connects all person with constant number of sequential execute operation, whereas RNA requires OF in sequential operation. Um, Let me just. What is the time complexity of self-attention? What is the time complexity for transformers versus LSTM? I don't know what time complexity, but n is a sequence length, n square into embedded dimension. Oh, so the longer the sequence length, hmm, I think the sequence length is the same as context length, right? Okay. Transformers of n square into d. This is n into d square. Okay. For short sequences, LSTM is usually faster. For large D. For long sequences, transform become much more expensive. However, transformers are fully parallelizable. Algorithms are inherently sequential. So yeah, none of this matters, right? Cool. Uh, as a side benefit, self-conditioned yield more interpretable models we inspect attention distribution. I don't know about that, but sure. Training. Training data and batching. We trained, okay, this is they're talking about how they trained. And we have P100, I'm sure. Big model were trained for 300 test steps, 3.5 days. So that we can train the GPTs in hours, only less. Optimizer, they use Adam. Regularization, um, they do residual dropout. Label smoothing. During training, we employed label smoothing value of 1. This hurts perplexity as the model wants to be more unsure but improve accuracy and boost score. Results. Okay. Conclusion. In this work, we presented the transformers. The first sequence transaction model based entirely on attention, replacing the Arnold. Okay. For translation tasks, they performed very well. Task, the former tasks are best model outperform all the previous report and samples. Cool. We are excited about the future of attention-based models, and okay, yeah, it is exciting. Making generation the sequential. Okay, sure. Yeah, I think that's it. Yeah, this is a good representation for how different words are attended. Right. So yeah, I think that's it from me also. So I'm actually thinking about reading more papers. So I will be reading more papers, foundational papers related to LLMs. After the foundational papers, I want to like get to the more survey papers, recent survey papers such as this, right? So this talks about the recent mix of experts, things like that. So we'll read that too. And unlike this paper, I have read this paper multiple times. That's why I kind of skimmed through the paper. Plus, I knew a lot about the paper, so it was a very fast read, right? Uh, yeah, you don't read attention all you need in like 1 hour, at least for the first time. So yeah. So thanks for watching. We'll continue this thing. Uh, yeah, yeah. Bye bye.